Welcome back to Groundhog Graphics, and as per usual, I'll be working in Power C, and I am continuing where I left off from my live stream, and I'll be working on multicolor mode pixels, getting those put on the screen. So let's go ahead and get started. I'm going to start by editing, or actually I'm going to start just by showing you what I left off with. So MCM, PXL percent, and this will show you multicolor mode pixels on the screen. Just a line for right now. I still have to work on plotting the X and Y positions. But we have the line, it's multicolor mode. You can see this color, maybe it's cyan, and hit enter, it's yellow, red, and then the next one will be the background color black. And then we hit this again, nothing. Hit this again, clears the screen, but it was already clear, and back to text mode. So now, let's go into the source code and see what I need to work on next. MCM PXL percent dot C. See this G mode function? So I'm setting my multicolor mode right here, setting the Vic bank, setting the bitmap to the upper 8K of the Vic bank, and setting the text bank to 1, which puts it essentially, if the Vic bank was at 0, text bank would be located at 400, which is a default. Then text mode puts us back into text mode so we can see the shell, and we can go and edit and all that stuff. So it puts us back at default. And make tables is where we make the tables to reference where the dots go, because this is the C version that I'm going to, once I figure out the logic here, I'm going to convert it over to assembly, and then once I get the assembly version finished, then I'm going to bring it back in an assembly version for Power C, so it's a lot more faster and it will be more compact. Because there are, like I've said before, there are graphics libraries for Power C, but they are either limited by resolution, or limited by graphics mode, or limited in the fact that they're written in Power C, which makes them very large and of course slower. So there's limitations. I'm trying to get around those limitations and make a more versatile graphics library. But like I also said before, I'm not really intending this for games right now. I'm intending this so I can make other programs that will utilize some graphics. But right now, games are not really my focus. But anyway, make tables is for the reference, so I'm kind of making this in a way that I would need to use it for assembly. Otherwise, I could make this code a lot simpler. We wouldn't need these tables and things. Or I could actually I wouldn't need so many tables too. But we have these tables here, and then we have a plot function, which is something we will likely be working on in this video, which is getting the X and Y and the color plotted to the screen in some kind of efficient manner, and then probably call it success at that point. So let's see what we have so far. I have this stuff remarked out. I'm not using that. That was for printing the tables. Keep it there for debugging if I need it. Set the graphics mode. Set the colors of the screen. And set the pixels near the left side of the screen. And that's what we saw, that bar. So this is where we're at, and this is what we want to change. So now we know we are in multicolor mode. And we know we got pixels on there. We need to change this. So I'm going to cut this out. F5. Start here. Come down here. paste this back in as old code. Probably will not need to use this again, but I'll just save it here temporarily. We may end up using this, that's why I saved this too. This would put pixels on the screen using the plot. Actually, we might just use it right now. Turn pixels on. Oh, it does all 3 colors. And turn pixels off. Okay, so yep. Let's pull this out of cold storage and bring it back up here. So this should draw pixels at a diagonal line to X and Y 159, so it won't come down to the bottom of the screen, because the bottom of the screen, the vertical, is 199. This should go all the way across, 1 dot shy of the right border, because in multicolor mode our resolution is 160 by 200. And then this just does the same thing but changes the color. Same thing, changes the color. Have a break in between each one so we can see it. And then this one turns the colors off, does the same thing though, just using color 0. So 3, 2, 1. Alright, well, let's see how this works at this point. Let me check for any syntax errors. Warp mode that. Syntax error found. Temporary storage, that's why. Turn pixels on, and that's another problem. Okay. And that's why we use the syntax checking editor, so that way we don't have to exit out, start compiling, and then find the problem. When I can fix this before I have to exit. Background color. Turn pixels off. And check this again. Syntax error again. 4. Set pixels near left side of the screen, and this is why. And check one more time. Hopefully we get no syntax errors. And we're good. So now I'm going to pause the video. I'm going to do the compile and link, and then we'll execute it and see what we have. Compiling and linking is done. Now let's go ahead and run it and see what we have. It probably won't work, but we'll just see. PXL, part of the debugging process. And basically the same problem I had before I fixed the multicolor mode issue. So that's fine. I think I'm shifting pixels too far over is what I suspect is going on here. Let's see. The colors are changing though, which we didn't have before. And the background changed. And there it is. CED MCM PXL percent dot C. Tables. I think it's in our plot command here. It's probably in this line right here, probably. Alright, so I'm going to show you how this is supposed to work. I'm going to bring up the calculator on here. And you see this little formula here? This is our X resolution, and I AND it with 3. So let's say our X resolution is 0. All the way, first pixel on the screen. Okay, so it's 0. First thing we do is we would AND it, which you know what this will probably come out as, but we'll just follow through. AND it with 3. There's 3. That equals 0. Then we would exclusive OR with 3. And that would give us 3. Then we will shift it over 1 space, and that gives us 6. 6 is the number of times that our color value needs to shift over to the left to be the first pixel. Let's say the color, and mind you, we're going to set the very first pixel. The color is, let's say it's 3. So let's see what happens when we take 3 and we shift it over 6 times. What we get is clear entry. We have 3, and we go 1, 2, 3, 4, 5, 6. That's the most significant digits, bit 7 and 6, and that would be the very first pixel on the screen. So this formula should work, with the exception of maybe I need to add another parenthesis here. Could this be causing the problem? I just don't think so. But there it is. I'm going to keep looking at this, pondering this for a second, and see what I can come up with. So that's all I can see is potentially wrong, is that parenthesis. So I don't think that'll fix it. But I'm going to go ahead and compile it, and we'll test it, and we'll see what we have. Alright, let's see what it does. I have to do the same thing it did before. And it does. So something is wrong still probably in my logic on this. But if we did start at 0, 0, 1, 2, 3 seems to work. If you notice the very top left corner, pixel 0, 0, 0 for x0, y0 is there. And it almost looks like maybe pixel 4 is being set. And everything's done the same thing on that. Almost looks like that. And at the bottom, we notice we have, at the very bottom of the screen, not the bottom of the screen, but the very last pixels, at the end of this, we have 4 pixels. And then we only have 3 here. Only have 3 there. All the rest of these are 4. Just looking for any kind of indicator as to what the problem might be. But I notice right here, top left, pixel 0, 0, 1, 1, 2, 2, 3, 3 seem to work. If we have pixel 0, 1, 2, 3, this is pixel 4. Look at that. It is pixel 4. For some reason it's doing it twice and drawing it over there. Colors are working. Okay. MCM PXL %.C. Why is it doing this? We have a table here. And presuming our table's okay, for now I'm just going to assume it's okay. Parenthesis made no difference. Take that out. And we're doing twice here. What we're doing is clearing the dots and then setting the dots. I see no problem with that. And we turn the pixels on, we wait for a key press. So this draws all of them. Plot x comma 1, x comma y comma 1. But we're getting double lines. We are getting double lines, but we are also getting the right pixel locations. And then we're also getting the adjacent byte. And that's turning on too. Huh. That turns pixels off. Okay. Go back to the plot routine. Shifting over C. This is a character pointer. And equals C. Okay, give me a moment here. I'm not seeing it right. I'm not seeing the problem right off the bat here. Since we're getting those lines separated, and then there's also gaps vertically between them, I'm not going to draw all the way to 159 on the very first one here. I've made it 4, so it's going to be 0 through 3. I want to see if just the very first 3 dots come up by themselves normally. This would indicate there's probably a logic issue I have with my pixel table. So I'm going to go ahead and compile this, run it, and we'll see if we just get 0 through 3 dots on the screen without the double lines. So 1 second. Alright, let's see if we get just 3 dots. And we do. And the dots are in the right place. So then the rest of them do their thing. And we're good. CD, MCN, PXL, %.C. So I think we have an issue with the table. And the reason why they didn't clear on the screen before, because I run this out right here, which ands the pixels, which would clear pixels. So without that, none of the pixels that were currently on the screen would get cleared. Now they'll be cleared again because this routine seems to be working fine. Go down here to main. One more little test we can do is make this go to 5 and then take a quick look up here at these tables and see if there's any problem I can spot with my logic in this tables right here. I don't know if this is the right answer or not, but I'm looking at this X table and I see the columns times 4 plus X. And what this is let's say we're setting the very first element of X table, which we know would be 0. Okay, so the column starts off at 0. X is 0. And we do column times 4, which is 0, plus 0, which is 0. X tab 0 equals 0. Then that'd be column times 4, which is 0. But then if we want to we go from 0 to 3 for our X, we would still be in that same first byte. From 0 to 3, we would still be in the same first byte. So column times 4 plus X, that would be 0 to 3, it would still equal 0. But when we go to pixel 4, we need to shift over to the next byte. And I am doing column times 4. So when we go to the next byte for x4, right here for dot 4 horizontally, when we go to the next byte, I'm doing column times 4, which only puts me 4 bytes, a 4 byte difference. It really shouldn't it be 8 bytes? Because we have the beginning top left goes 0, and then it goes down. So it goes, let's see if I can draw it real quick. So we have byte 0, byte 1, byte 2, byte 3, byte 4, byte 5, byte 6, byte 7. Then, for our next X position over, this would be pixel 4, we would have 8. And then we would have 9, 10. So I'm thinking is I need to multiply it by 8 instead of 4. Maybe that's the problem. I don't know if that was a good explanation, but that's the best I can do on the fly right here. Let's try column times 8. And then let's see if that fixes it. Put MCM PXL %.C. And I'm going to go ahead and just do one compile and link with you guys, so that way you guys, if anybody's new to the videos, they can see how it works. Quit CC-P is because I have 2 disk drives, MCM PXL %.C. Now we compile, and this is why I paused the video, so I'm not going to show any more compilation or links in this video because it's too time consuming. And I don't think anybody wants to sit here through it. This is how long it takes to compile C code on a Commodore 64. Now, not my Commodore 64 that I have out in my living room, that I can't capture the screen on, so that's why I'm using the emulator. I have a super CPU on it, so it does move a lot quicker than this. I bought the super CPU specifically to speed up compiling C. Yep, still saving the file at this point. The Super CPU, however, does not play nice with the Assembler Turbo Macro Pro, unfortunately. There's problems, there's a little bit of conflict between the two. So I've noticed. Then to link, normally you would type all this out, but at the end of my source file, I typed out the linking process. I even typed in this, all this is from my source file, output file name, all this I typed in beforehand, so all I have to do is come to the top. And for right now, this is working. All I do is hit enter, 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 and just go through it. But as I recall before, I've done this before and there was some problem where it didn't work, but for right now, it's working. All I do is I just hit enter. I have to go one line above to start. Then I hit link. Linker gets loaded. O file for MCMPXL gets CH. GG.L. And this will be the core C files with the up arrow, which on my Vice key map is delete. If you need a copy of my key map, it's on GitHub for Vice. It's a symbolic key map. There's the core files. They're getting linked in from device 9. Device 9 on my emulator is a 1581, like my real computer. And they have no disk drive sounds for 1581. in Vice. So now everything's linked in. Hit enter on that. Come down here. You see how output the capital O changed because I messed that up. It wasn't no capital O. It's a lowercase o. And the name is already in there to be overwritten. Push enter. And that is linking and creating our executable file. Executable files end with .sh. And then to execute, MCM, pxl, percent, and C. Well, what is this? 1, pixel 2, 3, 4, and 5. Well, look at that. Let's see what the next routine does. Oh my, doesn't that seem to work? Well, I think we fixed that. Very nice. Very nice. So there it is. Pixel table is now working. So that was just a little bit of oversight on my part, but we've got it working. And this is why I'm doing it in C first, and then we're going to move it over to machine language, because assembly is even more difficult to work with. Well, at least for me. Some people maybe find it even easier. I don't know. And one thing you can say about assembly, it's a heck of a lot quicker to assemble some code than it is to compile in C. CED, MCM, PXL, percent, .c. So we fixed that problem. So for X table, it needed to be column times 8. That's what fixed it. I had column times 4. Very good. And column times 8 is very similar, but it is a little bit different than the high-res X table. The Y table is exactly the same as it is for high-res or multicolor mode. This, I don't believe I changed this. So this Y table is the same. The only difference is for high-res mode, I needed a second Y table, which I named Y table H for Y table high, and that was to make up for the extended resolution. The resolution from 256 to 319 is larger than a byte, so I needed another Y table. But for multicolor mode, the 160 by 200 all fits within a byte, and I only need one Y table, and both of them only use one X table. So there it is. That's fixed. That's great. This down here is still interesting. There's a lot going on in here to get pixels on the screen, and I would imagine this is probably using more cycles, CPU cycles, than I would need. Possibly I need to make another table to reduce some of the cycle usage here to draw a pixel on the screen. But like I said, I'm not making video games right here, so I don't know. We'll see how it works. I'll try to make it as efficient as I can. I definitely will try to make it as efficient as I can, but I'm also not overly worried about it. But we'll see what I come up with. That might need more, might need a pixel table to stop us from having to do this ANDing and XORing and all these shifts, because these shifts, it would be 6 shifts just to get the color over to the most significant digits in a byte. So that's a lot of shifting too, and that would be in some kind of loop in machine language. So, but anyway, so plotting works. This works. Our very first one went to 5 or 4. And then we can just do 1, 5, 9 like all the rest of them. Background color D021. We clear screen to 56. I'm kind of curious. When I change this background color, is it actually changing the entire background instantly? Let's get rid of the clear screen. Let's see if that register just changes at all. So now there is no clear screen after our last line of pixels. As a matter of fact, let's just rem out all of this so we can actually see the pixels still on the screen while we change the background color. That would help. Turn pixels off, get CH, that's all out. Run a syntax check here. All looks good. Put to disk, MCM pxl %.c. Quit. MCM pxl %.c. Compiling, and I'll pause. And we are recording again, so let's go MCM pxl %. Let's see what we have. See if the background screen color changes or a pixel is still on there. So we're not going to erase the pixels. So we got the first color, second color, third color, and background change. Sure enough, that's cool. So from high-res mode, you can't change the background screen color that quick. But for multicolor mode, you just set register D021 and your background color is changed. That's pretty neat. And there we go. We're out of it. Very good. So now, you know, it's got me thinking, and this is why I wanted to program this in C. CED, MCM, actually no. Let's do pixels %.c. Let me show you something. It's just a thought I had. But it could be wrong too. So, but here's what I'm thinking. We create our tables for our high res, right? And we got our X tab, and it's column times 8 plus X, but it still equals column times 8. So rather than making two different tables, a high-res table and then the multicolor mode table, and rewriting all that code, let's say we make a high-res table, and then we basically cut it in half. We do another routine just to kind of shift half of it over. And we end up making a multicolor mode table just by shifting it, so we don't have to recreate. I don't know if that would work out better. I think it would work out faster just to modify the high-res table that is to make a new X table, possibly, because I think we can just shift it over, because we're doing column times 8 for 8 pixels, but then we have 4 pixels. So if we were just to shift it all to the left a little bit, halfway, we would end up still having column times 8. All that would still be right. And it could be a pretty quick routine just to modify our X table. And even then, once we write the table, if we wanted to go and do high res again, we could just maybe shift it back over to the right again. So maybe we would create one table and then shift it left and right depending on what graphics mode you're in. If this is any advantage, I don't know. Maybe. But it seems like it maybe could save some code, save some space by doing it that way. But I had to think it through, and I guess we could try that by copying this F5, F6, clear this out, get multicolor mode pixels, pxl %.c, go down here, F5, F6, there's a high res, and then see if I can make another routine to shift this over and see what that looks like. So 1 second, let's see what I come up with. Okay, no, I don't think that would work. I was gonna shift it over and move everything 4 pixels over, basically in the X table, but then I realized that our X table for the high res mode doesn't actually go for the full 320 resolution. Half of 320 is 160. That's multicolor mode. So without having the full 320 in our X table, if I cut that in half, I only come out with 128 pixels, which leaves us actually short minus 160. Leaves us short by 32 pixels. So it looks like we still have to make a new X table for a multicolor mode. That's okay. But it was an idea. So now, let's see what else we have here. So we can get rid of this, because I know that's not going to work. F5. Go down here to the shift I was getting ready to start writing. Cut that out. So there's our X resolution table. So now I need to start thinking about what we're going to do with plot to see if we can improve this a little bit. So here is our pixel table. Multicolor mode, PX tab with 16 entries. Okay? We have 4 colors and we have 4 possible pixel locations. 4 times 4, 16. Then instead of populating this table in here, like I could have done these, but it would be just too difficult, I just wrote a routine to populate it. However, in assembly, I will just hard code this. But MCM PX table 16, and when we go down to make tables, I have added for colors 1 through 3, it creates a pixel table. And what this does is the pixel table, well, actually what it does doesn't matter right this second, because I actually also made a function, or wrote down some code to print this table out, so you'll see what it does. But it goes through all the colors, all the possible X positions of the pixels, and then that's between colors 1, 2, and 3, and then color 0 is actually going to be inverted from the MCM pixel tab color 3, because color 3, that is 2 pixels set to 1, so it will be the inverse, because in order to clear a pixel off the screen we would use an AND, so it actually would be the inverse of 3, color 3. So that's what this one does. So it creates the 0 pixel table from the 3 pixel table. And what we do is we shift the color over left twice. Let me show you this. Get the calculator, and let's say we have binary, we have 3, color 3, okay? And we want to get to the color 3 pixel table. So what we do, shift it over 2 times, and that puts us at 12. The index of 12, 13, 14, and 15 will be the pixel table for the color 3. That's the last tail end of that table. Look at when we do this. If we do for color 1 or color 2, let's do color 2. We shift it over twice. Puts us at 8, 9, 10, and 11. will be our pixel table for the color number 2. And just for the heck of it, put 1, shift it over twice. Now we're at 4. So 4, 5, 6, and 7 will be the color table for the pixels. For color 1, it will be the pixel table for color 1. And then the zeros, well, that would just be 0. So what we actually would need to do is do the inverse. So let's say the leftmost pixel 0, we would have zeros, and so we do 1, 2, 3, 4, 5, 6, and you see the leftmost 2, these would be zeros, so we can AND it and clear that dot, because color 0 is basically background color, that would be clearing it. The rest of these would be 1s with because we're performing an and that would leave all the rest of the pixels unchanged. Let's go ahead and see if my pixel table is right. Let's do a check, syntax check, see if there's any errors here. Nope. Put this to disk. MCM PXL %.c. Quit this. MCM PXL %.c, and I will compile it. I compiled and linked it, but I need to include a function I just made the other day in assembly, which is bin string. That way I can display the binary output of our table. So I'm going to copy. I'm going to mount to drive 10, PClib02, I believe. Bin string right there. Or actually, Alt 0, PClib01, right? Do we have it? Yeah, I have bin string on there. So I will copy from drive 10 to drive 8, bin string .o, and that converts a binary, a byte, to a string in base 2 format. So overwrite, sure. Now I link MCM PXL %.o, get ch.o, gg.l, and if I don't do anything else, you see bin string is an unresolved external reference, bin str.o, then the core routines for C, work mode that, dupe string. Oh, so this is the wrong, this might be the wrong bin string. 1 second, and we'll be right back to where we were. Okay, so I used an old version of my bin string. I deleted it. Now we can link the new version. So it will be, hold on a second, I need to change the work drive to 8, link, and then MCM PXL %.o, gg.l, get ch.o, bin string.o, warp mode, And now all of our external references should be taken care of. Yes, they are. And MCM PXL %.sh. So this should now print out the new pixel table I made. Assuming it's right, then we'll see what I was talking about. MCM PXL. We'll see the whole pixel table in binary. Let's see. There it is. So color 0 is wrong. That's all ones. So, okay. Color 1 is right. Color 2 looks to be right. Color 3 is right. It's just color 0. That's the one that's wrong. Very good. And just go fix that. MCM PXL %.c. See what I did wrong with this. It's pretty handy being able to print out binary numbers when you want them. That's why I like that bin string function. Bin string and string bin, converting back and forth. Very handy to have those. Make tables. Right here is our 0. So x equals 0, x less than 4. X here's fine. And we take 3 and we did it with FF. And I know this is an unsigned number. In machine language or assembly, we would be dealing with a byte. But in here we have 2 bytes. I should have flipped those, though. MCM PX tab 3. XORed 0FF. We could do that. Shouldn't be necessary. X equals 0, x less than 4, x plus plus, x, tab 3, 0, 1, 2, 3. No? That's the problem. I was saying that doesn't seem right. 3 plus and 3, right. 3, that's wrong too. Yeah, that's wrong. Okay. That would be 3 shifted over 2 times plus x. That should fix it. Put MCM PXL %.c. This, compile, PXL %.c. Alright, ready to run, and hopefully the pixel table 0 will be fixed for color 0. Color 0, yep, now it's working fine. And that is our pixel table for 0, the inverse of 3, color 3. And that's what we need, because we'll be ANDing with 0, but everything else will be an OR. Actually, it'll be an and an OR. But we already have that in our plot routine, because you will have to clear a pixel. Because if you were to write to the screen, let's say the screen already had color 2. Pixel was set for color 2, and let's say you want to go, oh, I want to put color 1 in the same spot. If you just ORed it, you see color 1 right here. You would actually just turn the pixel from 2, you would turn it into 3. But if you actually want color 1, you would have to AND it with 1, clearing this bit right here. Then you would OR it, setting this bit right here, and then you would get your color 1. So to do multicolor mode pixels, you have to and OR it. And OR. That sounds weird, but and OR. So, and then this is just an and for zeros. That would just clear each 2-bit positions, or each bit, or each dot, each pixel. Because each pixel is represented by 2 bits. So 0, 0, 0, 0, 0, 0, all the way through all of our little pixel positions. Pixel 0, 1, 2, and 3. There's our table. And now, CD, MCM, PXL, percent, dot, C. So now we scroll down here. We know our pixel table set up okay. So now we should no longer need all of this right here. By shifting color over twice to the left, we should be able to reference our pixel table. And currently we are doing an exclusive OR, and then shifting up to 6 times. And now we can change that to just shifting 2 times. So let's clear that. Temporarily reference it out. And put in here MCM. Matter of fact, yeah, MCM, PX tab, X. Of course, we're going to have another and in here. And 3, right? Yeah, is there really much advantage to this? Because we still have to shift C, and we still have to and X. The only thing we're not doing is an exclusive OR. That's it. Is it really worth the pixel table? Now, of course, to some people, like, yeah, of course, you're saving some cycles, but to me, is it worth the extra bytes for a pixel table to save that? Because, like I said, this is not for games. I mean, I might rather just have an exclusive OR in there. Well, let's just see if it works, but I think that this may not be the route to go. X and 3 plus C. Or do I need to shift it? Let me see what we're doing here. So we did X and 3. What goes 1, 2, or 3? And then we need to do our color. The color has to be shifted over. So we're really not saving a lot here. Thought we would save a little bit more with this table, but not seeing it. I'm saying I'm seeing one exclusive OR. It's like, I don't know if I'm worried about that. C shifted over twice. Yep. It should be right. MCM, PX tab, X and 3 plus C. I'm thinking we're going to test this to see if it works, but even then, I don't think I'm going to stay with this. Because it's not worth having 16 wasted bytes to save a few cycles. Not important. Not that important. And I'll see if there's something else I can think of here, but so far I'm like, no. Put this to disk, MCM, PXL, %.c. Yeah, I'm not seeing this being worth it. I'm not trying to do bleeding edge speed here. Quit, compile, MCM, PXL, %.c. Alright, let's run it. MCM, PXL, %. See if our dots still draw properly. No. No, they do not. Interesting design, though. That's pretty cool. I don't know what that is. But looks like barbells at an angle. Neat. And then different colors. Oh, cool. Well, that's... And look at the different colors. That's pretty. I mean, for a bug, that's pretty fun. Yeah, I like that. It's actually kind of neat. Cool. That was a neat bug. Alright. Let's go in here and figure this out. But you know what? Maybe I'm wrong. Maybe there's still value in this table because I'm not having to do shifting up to 6 times. Perhaps that is the saving grace of the table. CED, MCM, PXL, %.c. Maybe that's what will make the table worthwhile. It's not just one exclusive OR, it's also several bit shifts. So what are we doing wrong here? Let's see. 3 shifted over 2 times plus X. Let's make our table. This is down a plot. I know our table is being made fine. So XN3 plus C. XN3 plus C. C shifted over 2 times. Let me think about this for a second. Maybe you need to put some parentheses in here. Maybe the plus is being done first before the and that would mess it up. XN3 plus C. Shift it over twice. Let's try that. Alright, let's see what we have. Disk drive sounds went away. Pixel table. Ah, that was it. Just needed some parentheses in there, so it was doing the addition with the color before it was doing the and. Okay. Now every color works fine. There it is, so that works. MCM, PXL, %.c. Me too. There. We muted it. It's the media keys. I hate media keys. And every time I do my run stop on here, and if I hit the function key or something like that, it turns on media keys. And then every time I hit my function keys, it does some screwy thing with audio or whatever, which is something I totally don't need, never have needed. And I have to keep fighting with this media key thing. I hate media keys. Can't stand them. Why can't we just have function keys? I don't know. Who uses media keys? Definitely not me. Let's see what we have here. So our pixel table works, plot's working. So we shift this over twice. Is the X table worth it? We shift that C over twice. So it's going to be two, ASLs. Then we do X and 3. But we don't have to. We don't have to do the addition in machine language. I don't know if it's worth it. But there's two ways to do it. And so I'm going to keep this way and this way. And when I write this in assembly, I can figure out which one I like better. So now we've got pixels drawn to the screen. We got a pixel table. Optionally may keep, may not. I'm thinking we probably will. It might save enough cycles to warrant the extra bytes. Dots are drawing. Printed out our little pixel table so everybody could see that. And I'm going to say that I think for this video, I think everything's working. It's a good place to conclude this video. Not to say that I'm stopping working on this, but I think going to the assembly part of this should be the beginning of another video. So I will stop it now and probably just instantly start making the next video. So I will thank everybody for watching. I hope that making a video and cutting out some of the extras from the live makes it a little bit better and more tolerable for people to get through. And I will see you in the next video. Bye.